This is video help for problem 9.5. Here we've got a spin echo, that is we've got a pi pulse. After we've excited, and what we're going to do is we're rotating around the x prime, and we know that if we go 90 degrees, pi over 2, we are lying along the y prime, and let's call that phi equals 0, and that will be our initial condition at t equals 0. And we precess, remember, clockwise, looking down from the z, which means that phi will go negative. You know, phi is the usual azimuthal polar angle. And so it's going to go negative as we precess clockwise. Well, you know this story. We're dephasing, but then, you know, the different spins fan out. You know, some guys are behind others, and this pi will flip them over. And now the fast ones are behind and the slow ones are in front, and they'll come back together. They'll come back together another time tau later, if that's tau, and we have an echo at 2 tau. Let's put that 2 tau right on top of our gradient echo. And what's different here from, you know, the text is we just have this dephasing gradient lobe before the pi pulse, in which case we can have it, you know, we'll have it actually as a positive lobe because this will change the sign on it. And we'll see this is going to give the same answer as in the text. Well, first of all, fundamental thing, our precession is minus gamma b. Our b is add the whatever magnetic fields. You add the fields, so you add the phases, and you just superpose them. We've got some kind of inhomogeneity that doesn't depend upon time. It's independent of time. So this is kind of an external non-uniformity. Remember, we can't get rid of fundamental T2 because that's oscillating in time, changing in time. But when it's not changing in time, we can use a spin echo to cancel this and recover a bit of our signal at 2 tau. Well, we've got a gradient here too. Depends upon time because we're changing its sign in order to get a gradient echo. We have a dephasing, and then we change the sign so we can rephase, and we'll rephase right at the same place that we spin echoed, our gradient echo and spin echo at the same time. In part A, we're asking what is the phase? The formula is given, and then also there are formulas given in the homework hints, so that there's so many formulas given, I just want to talk it through. You don't need formulas here. What is the phase in between T1 and T2? In other words, between here and here, what is that ultimately? Well, we got to take into account the phase evolution here, flip and evolution, and dephasing from that. Somewhere in this interval here, before we go to the positive gradient lobe. We start out by looking at 0 less than t less than tau minus in here. You know what that is, minus gamma delta bt. Then at tau plus, that gets flipped. That minus gamma delta b tau, the phase that we got to right at the end of this thing, gets flipped, goes minus itself. And then we evolve some more. Now between tau plus and T1, right after this pi pulse to T1, gradient hasn't come in yet. And all we're doing now is just now coming back and rephasing a bit after this pi pulse. And you know this fundamental answer in this region here. You know it's going to be proportional to t minus 2 tau. Somehow, t minus 2 tau, so that it will vanish at t equal 2 tau, and you know what the full thing is. Then, going on, this is the delta b part. There's no gradient in here. In t1 less than t2, the delta b part just keeps going according to t minus 2 tau. And we now just simply do the gradient integral from T1 to T. And you can see the answer at 9.43 or 9.42 old. It just sits there and there's nothing more I need to tell you about that. Part B says, okay, now let's go for a greater time. Let's climb and start looking at the evolution of the phase right along the positive lobe between T3 and T4. Well, now we have officially the whole integral in getting our phi, the whole integral between T1, when we first turn on a gradient, out to time T. And of course, it has two parts. The first part is just what we had up here, except this part here now just goes from T2 minus T1, this integral, full integral from T1 to T2, and then we do the rest of the integral from here. I've got this part going here, and then now I've got the rest of this part from the positive lobe, from T3 to T. And that will give you this expression. Just gather these two G terms. You can check the answer against 9.44 or 9.43 on the old edition. And notice this will help. Where's the echo? It's 2 tau for the spin echo. But of course, we've arranged tau and 2 tau to equal whatever it is here. So what is the echo? What is the gradient echo? It is T3, this total time T3, plus half this distance. And how is that related to T1 and T2? Because this will help you when you're after you've gathered these terms together. You know how T4 minus T3 is related to this. I won't even say it. However, the answer just writes it in terms of, just writes this thing out in terms of T1s and T2s and T3s. But you could rewrite this whole thing. You can get the whole thing, every term, to be proportional to T minus echo time. And both the delta B part and the gradient part, and you'd echo together. And this is really nice to have this fundamental story understood for later discussions.